Welcome to The Explainer. Today, we're diving into a massive, looming crisis in the world of artificial intelligence. And honestly, it's all about energy consumption. The modern AI revolution we're seeing, it is incredibly power-hungry. As our deep learning models get bigger and bigger, they're literally slamming into the harsh, physical limits of traditional computing architectures. We're talking severe bottlenecks, processing power, efficiency, and sustainability are all taking a hit. Basically, our current computers, no matter how advanced they seem, are fundamentally struggling to keep up with the real-time complex workloads that next-generation AI demands. So you gotta ask, what if the answer isn't just building another giant data center, but actually completely rethinking how a computer is built, right from the ground up? Well, it turns out the solution to this massive computing bottleneck might actually be sitting right inside our own heads. It's a fascinating field called neuromorphic computing, or sometimes you'll hear it called neuromorphic engineering. Instead of just forcing new software to work on old, traditional hardware, researchers are designing hardware and software that directly simulate the neural and synaptic structures of the biological human brain. It's an entirely new, deeply brain-inspired computing paradigm. In this explainer, we're going to map out the evolution of this technology. We'll start with the AI energy problem, then move into how it's inspired by the brain, and get into spiking neural networks explained. After that, we'll hit hardware milestones and chips, explore real-world applications and impact, and finally, wrap up with the future of computing. Okay, let's dive into this with Section 1, the AI energy problem. To really grasp why we even need these brain-inspired chips, we first have to understand exactly why our current technology is holding us back. So the crucial thing to understand here is something called the von Neumann bottleneck. Look, most computers today, from the smartphone in your pocket to those massive cloud servers, they use a von Neumann architecture. In this setup, the memory unit, where all your data is stored, is physically separated from the processing unit, where the actual math happens. So to do literally anything, a computer has to constantly shuttle data back and forth between these two units. It processes everything sequentially, just step by step. Now, this constant back and forth data movement creates a massive traffic jam, and more importantly, it burns an enormous amount of energy. Neuromorphic systems, on the other hand, flip the script. They integrate memory and computation together. They operate in parallel, and they only act when triggered by an event. The result? Ultra-low power consumption. Realizing these fundamental limitations with traditional digital setups, scientists began looking elsewhere, specifically to the extreme efficiency of the biological nervous system. Which brings us to Section 2, inspired by the brain. Now, this journey actually started way back in the 1980s. Tech pioneers like Misha Mahawald and Carver Mead began developing the very first silicon retinas and neurons. They were basically using the analog dynamics of silicon transistors to mimic biology. Fast forward to 2014, and we start seeing these massive digital leaps, like IBM debuting its True North chip. Then, by 2018, Intel introduced the Low-Hi processor, which was highly focused on edge computing. And that brings us to the 2020s, where we've hit a major turning point, the integration of gradient-based machine learning. You see, each of these eras completely necessitated the next, naturally evolving from those early analog experiments into digital powerhouses capable of running complex AI. A core part of this whole biological inspiration is plasticity. In the human brain, neuroplasticity is just the ability of our nervous system to modify its neural pathways. Neuromorphic chips mimic this exact thing through synaptic plasticity. Think of it like walking through a really dense forest, right? The first time you push through the brush, it's difficult, but the more you walk that exact same path, the wider and easier it becomes. In these chips, synapses adjust their weights, which is basically the strength of their connection, based on how often and when signals pass through them. So the hardware actually physically adapts and learns in real time to new stimuli. Pretty wild, right? Now that we understand the inspiration behind it all, let's transition to Section 3, Spiking Neural Networks Explained, and explore how these systems actually operate under the hood. All right, so the real secret sauce of neuromorphic computing is the spiking neural network, or SNN. They're widely considered the third generation of artificial neural networks. Now, unlike traditional neural networks that just process continuous numbers, SNNs factor in time. Imagine a bucket catching drops of water. The neuron accumulates an electrical charge over time, and it sits there completely idle, consuming almost zero power, until that charge hits a specific threshold. When it finally does, bam, the bucket tips over, firing a discrete electrical spike to other neurons. If the charge doesn't reach that threshold, it just harmlessly leaks away. This event-driven spiking is exactly what makes them so incredibly energy efficient. And this brilliantly illustrates the programming evolution we've gone through. See, for a long time, the absolute biggest hurdle for neuromorphic chips was just figuring out how to actually program them, because standard coding simply doesn't work on spiking neurons. Traditional CPUs rely on procedural, step-by-step code. Later on, tensor processing units, or TPUs, found huge success using gradient-based parameter optimization, which you probably know as deep learning. Well, the massive breakthrough for neuromorphic architectures recently was adapting those exact same gradient-based machine learning techniques. Using clever methods like backpropagation through time, engineers finally solved the monumental problem of training deep spiking neural networks, making them genuinely viable for general-purpose applications. With the programming side finally unlocked, let's shift our focus to Section 4, hardware milestones and chips, and look at the actual silicon marvels driving this computing revolution. Different companies and academic institutions have taken some totally fascinating, varying architectural approaches here. For instance, IBM's True North chip simulated 1 million neurons using a staggering 65 milliwatts of power. That is a tiny, tiny fraction of what a standard processor uses. Then you got Intel's Loihi, which takes an asynchronous digital approach. What's absolutely amazing about Loihi is that it completely removes the global clock that traditional computers use to sync up their operations, which just drastically reduces power drain. Then you also have systems like Brainscale, an accelerated machine using a hybrid analog-digital wafer-scale design, and Tianjik, a highly configurable hybrid many-core chip that's heavily focused on pointing us toward artificial general intelligence. Despite all their architectural differences, these chips generally share 4 core pillars. First up, event-driven computation, meaning circuits only activate when triggered by an input. Second, asynchronous operation, meaning they operate without that power-hungry global clock. Third, in-memory computation, which means storing synaptic weights right next to the processing logic to totally kill that von Neumann bottleneck we talked about earlier. And fourth, sparse communication, literally only transmitting data when absolutely necessary. Together, these 4 principles allow neuromorphic chips to break far past the physical and thermal bottlenecks holding back traditional GPUs. So we have the highly efficient hardware, and we finally have the software to train it. Now let's connect all this technology back to you in Section 5, Real-World Applications and Impact. The biggest reason why this matters right now comes down to a concept called Edge AI, or TinyML. Think about your smartwatch, remote sensors, or even your home security cameras. These are what we call battery-constrained edge devices. Normally, they have to send really heavy data to a massive, energy-burning cloud server just to process basic AI tasks. But neuromorphic chips' ultra-low power consumption means these devices can process AI locally, in real time, completely independent of the cloud. This saves massive amounts of battery life, protects your privacy by keeping data local, and prevents massive data center carbon emissions. It's a real win-win. The industrial and medical impacts here are already proving to be profound. In autonomous driving, neuromorphic vision sensors allow vehicles to make lightning-fast, real-time decisions in super complex traffic situations, all without relying on slow, frame-by-frame cameras. In cybersecurity, their swift computation makes them absolutely ideal for detecting the low-latency patterns of a fast-moving cyber attack. But honestly, perhaps the most amazing stuff is happening in the medical field. Neuromorphic hardware is currently being used to deeply analyze multi-channel EEG signals to decode brain activity, aiding in the early diagnosis of Parkinson's disease. They're also being applied to tactile prosthetics, accurately simulating biological neural activities to provide smooth, highly natural tactile feedback to users. It's literally life-changing technology. Let's move to and see how this builds into Section 6, the future of computing, where we look at the challenge of scaling the brain. While the potential is absolutely staggering, researchers definitely still have to overcome some specific engineering and algorithmic challenges before we see ubiquitous commercial deployment of this stuff. Step 1 is developing even more biologically plausible models of synaptic plasticity that can better integrate both short and long-term memory. Step 2 requires solving a major scalability issue by building high-bandwidth, low-latency communication networks between massive clusters of these chips. And Step 3 is achieving seamless hardware-software co-design, essentially creating accessible, easy-to-use toolchains so everyday programmers can build applications without needing a literal PhD in neuroscience. Now, if these challenges are overcome, the outlook is pretty monumental. The sources report that because of its massive parallel processing, real-time adaptability, and high performance, neuromorphic computing has the potential to serve as one of the foundational building blocks for artificial superintelligence. It is, quite frankly, a hardware paradigm that finally aligns with the incredibly complex, highly adaptive needs of next-generation AI. We have spent decades trying to teach machines how to think. Now, we are teaching machines how to physically exist like a brain. So I'll leave you with this to ponder. As neuromorphic hardware scales to unprecedented levels, will the next artificial superintelligence be limited by the algorithms we write or by the physical constraints of mimicking the human mind? Thank you for joining this explainer.